So, good morning, ladies and gentlemen. Good morning. Here's something not related to the course. 3 weeks ago, I have reported bad news about the beginning of war. Well, that is still going on. That's not that good. What is good, I finally got my friends and relatives from Ukraine here, and so my family has tripled yesterday's evening. But anyway, I hope I can manage and you all can manage. Good. How about our course? We did quite some hike. We have started from quantum mechanical description of single particle, and we built up description of many particles, topics of advanced quantum mechanics, and finally we came to the fields, to some summit, right? And we have exemplified this magnetism and superconductivity. So from particles to the summit. Now in coming 2 lectures, we're going to make similar hike, but with another starting point. Namely, we will start with classical fields, very different from particles in classical physics. And we will go on, and we will come to the same summit. Third, finally, in advanced quantum mechanics, there is no difference between particles and fields. It's just the single quantum concept. In other words, we are going to quantize fields, right? And that we do in 2 steps. Today, I will have to do some preparatory work for quantizations. So I won't mention quantum mechanics at all today. I will talk about classical fields, and it will go in the following way, a little bit complex. First of all, I make a claim that eventually I can quantize any field, and I define what is a field, what is any field in classical physics. Second, I will give a simple example of a field, perhaps rather strange one. We will talk about a system of balls connected by springs. Fine. We will see that these balls can be seen as a set of harmonic oscillators. Good. Then we take perhaps more important and physical example of a field. We will talk about electromagnetic field in vacuum. As such, we will have to recall many things which you know from electromagnetism. We will talk about Maxwell equations, quite a bit of stuff related to this. We will talk also about interaction, how electromagnetic field interacts with charges. And we also present electromagnetic field as a set of harmonic oscillators. Then we really take a very simple example. We will look at a single electromagnetic oscillator. Hope you remember that. You just take capacitor, inductance, make it together. We will look at this oscillator. Fine, that's what we are going to do. Let me start with a message. First of all, let me give a definition of classical field, which will fit any situation. A field is a quantity could be scalar quantity, but frequently it's a vector quantity. So I put A is index A, and A stat here stays for arbitrary. Right? And what's important that this quantity depends on coordinates defined in the space, and also depends on time. That's a classical field. Right. I would assume, although it's not really crucial assumption, we'll talk about dissipation in this course in quite some detail. But at the moment, it is convenient for me to assume that there is no dissipation in the evolution of this field. So it is governed by Hamiltonian dynamics. Right? And as such, it will satisfy these Hamiltonian equations, and that will define time-dependent dynamics of the field. We have initial configuration, and then it evolves. Yeah, for instance, if you think of electromagnetic field, you could see propagation of electromagnetic waves. Right, what are examples of the field? Can you perhaps come up with an example? Yes, okay, right, that is correct examples. In this case, we have a vector ring, which depends on coordinates and time. Also, we know, we recall, that electric field is related to magnetic field. So if it evolves simultaneously, there's magnetic induction. So one would have to pick two fields, electromagnetic and electric and magnetic. Some other examples? Temperature field? Yes, could be distribution of temperature. Usually it's dissipative, so we don't want to look at it at the moment, but yeah, as far as field is concerned, it's an example is sound. Yeah, sound, accent, sound wave. Sound, pressure. Right, for instance, in air, in atmosphere, then we have basically pressure. Pressure is a function of coordinates and time. And looking at the equations of hydrodynamics or aerodynamics, we can predict how does it evolve, what are the events. That's right. So it is custom to work with linear fields. For many things. First of all, many fields are really linear physically, like electromagnetic and vacuum. With high accuracy, it's linear. Good. Even if it's not non-linear, we can do what? We can do linearization. Theoretically, it means that you kind of skip the terms in your equations which are not linearized. Practically, what does it mean? It means that there is some ground state of the field, for instance, no field at all, and you look at small deviations, right? And the deviations are small, so that's what Taylor told us, Taylor expansion. You can always linearize. Fine, so we will quantize linear fields. And what is the message? One could think it's a boring message, but it's important for quantization and for guessing the universality of quantization. that very message is that any field can be seen as a large set of harmonic oscillators. And I kind of gonna do quite some technical work to show you this explicitly. Right, then other part of the height, although it could be difficult, it's rather straightforward. Because we can quantize single harmonic oscillator, and that means we can quantize many of them. Good, but we are not there yet. We still have to talk at large about classical fields. So let me give an example. Well, perhaps not the most obvious example, but it's, I think, nice one to understand how different the fields can be. Let me consider the system of particles connected by springs. And let me see what can I do for that. What can I do? Can I derive equations? And how can I do this? All right. What would be the most straightforward and convenient for us a way to derive this equation? Just write the Hamiltonian for the whole system. Good. So summation over n is a summation over all balls. Each ball has a kinetic energy. Here it is. P squared divided by 2n. And each spring, which is connected to two balls, those are the coordinates. Each spring provides elastic energy, positive elastic energy, proportional to the deviations of these balls from their equilibrium positions. So, how physical it is? First of all, you can make it. Everything that you can make is physical, you're engineers, right? Whether it occurs in nature, well, one can think of oscillations of atoms in crystals, in metals, and you think of one-dimensional chain of the atoms, and that's pretty accurate description of sound oscillations in one-dimensional crystalline systems. Good. Let us see. What do we do next? The rest is kind of automated. If we know Hamiltonian, we can build up equations of motion. Right, so derivative of time derivative of momentum is a derivative of Hamiltonian with respect to corresponding coordinate. And let's see, time derivative of coordinate is a derivative of the Hamiltonian with respect to momentum. So we always have pairs of variables, momentum and coordinate. Good. Then we applied, we write equations, and now I wanna make a little jump. I want to exclude momentum from these equations. How would I do this? Well, it's a simple, sir. X with a dot is proportional to this momentum. So instead of momentum, I substitute x dot velocity. Right. So that's what I have. This is actually proportional to acceleration of a given ball. And what is on the right hand side is a force acting on the ball. Fine, okay, it depends on positions of the neighbors. That's nature. So how we can deal with this equation? I will make use of the fact that all springs, all balls are eventually the same. And I will look for solutions for x in this form. In the form of plane wave, if you wish. So it has frequency with which it oscillates, and it has wave vector. Right? So the solution in this form is satisfied for any uniform system. What would I do next? I just substitute it into equation. And I see that the equation is satisfied if there's a certain relation between frequency and wave vector. What is this in this case? Well, I substituted here. I got the wave times second derivative. Each derivative gives me a factor of omega k. So I have omega k squared. Good, I substitute it into this part. Right, I have three exponents. They are shifted by one. And in these exponents is shifted by one. And I can calculate these returns to this form. Here. So it's a substitution of the solution into the equation. Fine, what do we do next? Just state what it is. There is interesting dispersion. Dispersion is a dependence of frequency on wave vector. Here it is. To be precise, we need to do some bookkeeping. We want to understand how many different wave vectors could be there in the system. Well, again, for speed and simplicity, it is convenient for me to close this chain to impose periodic boundary conditions. Right? What does it mean? That if exponent shifted by n atoms must come back, must be 1, that gives me possible values of the discrete wave vector. Right, length of them is quantization. All right. You might have reminiscence with solid state physics, optics with oscillations. In spite of some astro, it's all quite interesting. All right, so we have found a solution. I want to make next step, and I want to write general solution for this equation. That's where I need linearity of the equations. Because linear equations are really good. Any sum of two solutions is also a well-defined solution. A solution to the system of linear equations. Right, so to write a general solution, I just have to sum up all these partial solutions with different case, with arbitrary coefficients. So these use the amplitudes are parameters of this general section. Fine? Is it clear? Fine. So now in principle, I have all these answers, but I would like to rearrange it a bit to bring it to a convenient form. Oh, no, sorry. First of all, I would like to discuss a little bit. Yeah, we are talking about fields in continuous space. So let me elaborate a little bit on this model to show that it is valid in continuous limit as well. But what's continuity? You just close your eyes onto the details of the system, right? Suppose we cannot resolve the properties of the system at the scale of interatomic distance or distance between the balls. We would like to describe it in continuous limit. Okay, that's a kind of sketch an example. It's just a string, elastic string, which has some deviations, and we are going to write, do the same, write Newtonian, and proceed. There are some fine details in the difference between continuous and discrete Newtonian. There, I would say straightforward, you kind of replace summation over the bounds by integration over continuous variable x. Right, let's see what we have here. That's momentum in a given point, for a given ball. Right, what is this? Who can guess what this letter means?
Maybe particle density?
Precisely, it's a mass density. So in continuous, in a distribution, we have masses of individual bar. Now instead of summing over bounds, I sum up over x. So this is eventually mass of part of the string in interval delta x. So it's linear density of the string. Good, and right, here we also made it continuous. So instead of discrete difference, we have here square of the first derivative. Gradient of this displacement, u. Right, so this is elastic energy of the string. How do we make equations? In a very similar fashion. Instead of differentiation, we just vary. It becomes a variation of the Hamiltonian in a given point. Let's see. So the velocity of this direction, derivative over t. Here it is. Okay? Do we understand how to get from here to here? It's again always use of the thing of discrete model, right? Instead of integral, we write a sum, and we differentiate with respect to one of the terms in the sum with respect to given bound. Right. Similarly, we do with this part of the Hamiltonian. All right, what we have again, it's approximation, sorry, it is continuous limit of finite difference in previous slide. Okay, second derivative with respect to x. Right, so what we ended with is wave equation, very compact one. Second time derivative on the left, second coordinate derivative on the right. Right continuous limit of the string, and we see that there are waves in the string similar to waves of sound or electromagnetic waves. Good, let us try to find a solution. It can be found in the same way. A solution, a partial solution with a plane wave with a given wave vector and frequency. The relation between wave vector and frequency we can get by substituting this solution into the equation. So here we have this expression. Frequency is proportional to the first power of k, which means that this is sound. It's like sound waves in medium. General solution, okay. Again, the same. We just sum up over all possible k's. And each k has individual amplitude, u of k. The amplitudes, I should stress it here, are complex, but the total equation for x, total expression for x is real. So I have taken a real part of this. Good, so we have a general solution, and now I have the sensors in continuous limit, in discrete limit, and I want to do some rearrangement of the solutions. I want to see explicitly a set of harmonic oscillators. Right. I want to scale the amplitudes of the waves. So instead of displacements U's, I would have some letter D. And that doesn't look kind of obvious or illuminating. It's yet another ugly square root. We have plenty of ugly square roots in this course. That's one of the examples. Okay, why did I make it so ugly? Because in the next step, it becomes nice. If I redefine use in such a way, and if instead of use, I would substitute this in my Hamiltonian, that will take the following form. Standard form. So the Hamiltonian in this form doesn't have any information about elasticity, about masses, and the same, just about the set of frequencies. And all information is compacted into definition of. That's why, as we see further, it's good for anything. 4 elastic strains, 4 pressure waves, 4 electromagnetic waves. Good. Nothing to note if we look for equations for these, they really follow very simple time patterns. Each G complex number just is multiplied with oscillating base function. All right, that's also kind of shouldn't surprise you. because each UK oscillates with frequency omega k. Right. Okay, you may say, well, there's so many interpretations. Why don't your teacher want to go for another one? Nevertheless, believe me, it's going to be useful. So what I want to do now, I would like to arrange real two variables which represent real part and imaginary part of this complex number D. It's normal coordinate. So D is called normal coordinate. You can ask me why. My answer would be what's normality? Good. So it's normal coordinate. We take real part and imaginary part, and we call this generalized coordinate, and we call this generalized momentum. Okay, then indeed we express these in terms of these quantities. We put it into Hamiltonian and bring the Hamiltonian into this form. Standard form does have an information about the nature of the system, just like this. And you see that these quantities are indeed coordinate and momentum, because the equations are Hamiltonian equations. The equations can be derived in a standard way by differentiating the Hamiltonian with respect to momentum, with respect to coordinate, for each oscillator in this set. Well, equations are independent, oscillators are independent. Gets a bit boring. But anyway, let us try to proceed further. And let me switch the gears. Particles on the space. Now I want to do the same with electromagnetic field. Electromagnetic field is complex. When I was a student, it was kind of rather painful for me just to memorize all these Maxwell equations. I think if I wouldn't look at the transparency, I would have a difficulty to reproduce it after 40-something years of teaching. But anyway, let us look at it. First of all, it's good to understand that it's not actually that much, because Maxwell worked the whole life to write a single book that was really a thick book. And he has found 54 fundamental equations of electrostatics. Good people have read this book and they figure out that because one can simplify that, and they come up with 4 equations, which are called Maxwell equations. But Maxwell gave us 54 equations. And if you get to relativity, then we will see that actually Maxwell equation is just single equation, but just in relativistic tensor indices. Good, therefore, and what are they? I want to state, perhaps it was not stressed in the course of electromagnetism, that 2 of them describe evolution of the field. As we discussed evolution equations, you have a certain configuration of the fields. You can predict it what happens to the configuration on the next time step. So that's fine. That's evolution equations for electric and magnetic field. We have extra equations, conditions on this magnetic and electric field. So divergence of electric field is charge, and divergence of magnetic field would have been magnetic charge, number of monopoles. Monopoles don't exist. It was a problem in physics, but yeah, now we kind of know for sure that they don't exist. What I want to stress is green letters are sources for electromagnetic fields. So in principle, we could set configurations of density, charge density, and currents, and predict electric and magnetic field in each point at each time moment. There is a simple problem there's a little bit of a problem with this, because you have already noticed this. Who is not satisfied at this point? Is what I said. Not really. Okay, then let us discuss it later. Anyway, there are two quantities, electromagnetic field, red and blue. And there are sources, green things, which produce electromagnetic fields. What I want to do now is to make something illegal. Right? I'm old man, I have nothing, very little things to lose, so I can do this. I can do what I want. It is kind of legally compulsory to give you Maxwell equations in tricky French system international, which appeared to win the context for convenient system of physical units. But it's really ugly, especially in the field of electromagnetism. There's always some, there used to be some conflict in physical community. There are strong opinions. Say, my teacher in electromagnetism plainly told that System International is a graveyard of physical concepts. It's based on physics of the middle of 19th century. Good. This teacher is at the graveyard now. System International still exists, but I want to continue the tradition to do illegal things. So those are equations in CGS system. And look, they look a way simpler and a way more physical. In System International, we have strange things like magnetic susceptibility of vacuum, electric susceptibility of vacuum. I don't know what they talk about, right? In a good system of units, you don't have such fancy things. You have very physical, very fundamental a quantity, which is speed of light in vacuum. Good. So, as far as I'm concerned, it's more natural formulation of Maxwell equations. But again, I have to stress it's not really alternative. It just rewriting the equations in different system of units in a convenient form. Right, that was the only illegal transparency for now. I would try to stick to legal requirements. Good. In addition to Maxwell equations, there's a couple of useful relations. First relation, it's about really about interactions of charges and electromagnetic field. So there is a field, there is a force which charge experiences in electric field and moving charge, so this is velocity of charge, in magnetic field. If you really look deeply to first year physics, you can tell me what is wrong with this situation. Okay, what is that approximation? It is not relativity. Velocity of the charges are supposed to be smaller than velocities of light. But well, it's not because, yeah, it's good for the charges we know. Right, energy density, okay, that's no approximation of this. It just tells you energy which is accumulated in electric field. And you can always think of a capacitor with electric field between lines, and there's some energy accumulated with a capacitor. When I was a kid, I used to discharge capacitors between my fingers, really feel some energy coming from that. Fine, there's also inductive energy. If you put current to the coil, there's magnetic field accumulated, some energy accumulated due to magnetic field. So we can say there's energy density is proportional to the squares of electric and magnetic field. We will use it in order to write Hamiltonian, actually. Good, more relations, which will be useful for us. First, it's a famous pointing vector, which does not point anywhere. Confusingly, pointing is a family name. Right, it's a vector which actually points to the direction of energy flow. Funny enough, in electromagnetic configurations, there's any energy flow which is perpendicular to both electric and magnetic field. So the energy flow, it seems to be some process. However, if you just look at static configuration, electric field, magnetic field, all static, that would predict some energy flow. Right? That looks crazy. So what's the solution for this? How to put it into our hands ahead? Look, it looks like we have, if you just take electric field in this direction and magnetic field in this direction. So the energy flow above, why don't we collect it and use it to warm our houses? As answer that in static configurations, these flows, energy flows, are always circular. You cannot interrupt it, you cannot take heat out of it, you cannot take energy from this flow. Circular flows. Fine. And then there is a kind of a glitch of Maxwell equations, which is conservation of particles. One just take this Maxwell equations, looks at the current density I and the charge density rho seem to be independent variables. However, if you just put it in Maxwell equations, arbitrary configurations, and try to figure out electric and magnetic fields, the equation just stop. Like the computer gives you division by zero, some error message. So that doesn't work for arbitrary configuration. That works only if charge is conserved. So conservation of charge somehow is incorporated into Maxwell equations. In order for them to have the solutions, change of density, charge density, must be equal to divergence of current in this part. Conservation of charge. Good, I guess I'm done. Perhaps it's time for a break. Right, why don't we have 7 minutes break at this point?
But it's so weird. No, it's a rank too. I'm never going to say yes to it. I mean, I have fun, but I have raised. This is all necessary. The Lorentz transformations are also tensor in this notation. You can get the extra tensors that are concerned by doing Why don't you stay for But I was sure that the whole one I hope. Everyone's yeah. Well, that is right. Yeah, but I can try. Yeah. Just ask for all of you. Yeah, but we have to submit it by Monday.
Components of the this
I did the question and
Yeah, like the next exercise. Easier than like you can see what
so some of these units, some of these centers are
like minus or something. Yeah, that's correct. It's like you can see why.
I didn't say why we don't know.
Because everyone is saying, oh, I got the same for both, so I probably.
No, I didn't say that. I said that it was.
You got the answers. Oh, yeah. Oh, this question.
Yeah.
so confirming which one.
No, I saw there's like a group meditation.
On Sunday, yeah. Only
999 tries
Okay, which of these things should
Yeah.
would it be on course structure and examination?
Words like that.
Because I checked all of right.
Here, but it says, why are you can do homework together. Okay, but we can do together and upload each other.
No. I have a few quick questions. So first is practical, it's about the homework. Because it says on Brightspace we can do the homework for presentation groups. And does that mean we all have to hand in the document still individually?
Yeah, individually, yeah.
And can we hand in the same document? Okay. Then another question was about the SJ calculation, the speed of light, the value. I guess it has to change. But it's still the same as a.
Yeah, the system thinks arranged in such a way that Mr. CGS will be exactly meter.
And then last question was about the periodic boundary conditions. Because so far it seems to me that the only way we're quantizing the fields comes from somewhat arbitrary choice of choosing from periodic boundary conditions.
It's just more convenient curves. One can sit over the program.
And A is supposed to be the
One potential wave, so let's see what's the other wave.
towards it.
Or you could just go two walls. Two walls. Superpositions of two waves. This is not going to be it's a good one. Don't think of details. It allows you to speak. Good. Very good. Let's go on with our presentation. Let me again do some work. It is not a minute for me to talk about electric and magnetic fields. That's too many. And kind of correct formulation of electromagnetic field, of theory of electromagnetic field, involves potentials. In classical formulation, in non-relativistic formulations, there are two independent potential. One potential is scalar potential. It's like voltage in electrostatics. And another one is vector potential. So tell me the truth, who remembers what vector potential is? I don't want this truth, give me better truth. Okay. Right, so in principle it has to be in electromagnetism course. I don't know why it is forgotten. In principle it has to be here. Let me talk about this formally. One can present magnetic and electric field in a convenient form. Those are the forms. First, for electric field, okay, that we do remember, it's a gradient of electrostatic potential. In addition to this, there's a time derivative of vector potential. And magnetic field is a curve of vector potential. Right. So what's the use of expressing it in this way? In this way, two of four Maxwell equations are automatically satisfied. That equations with divergences. And right, the rest becomes of this form. So instead of four equations, we have only two, just for different variables. Good. That's good news. What could be, well, actually not bad, but let me say confusing news. Confusing news, I usually regard it as bad. No, I think they're good. Right? These A and I are unphysical values. We cannot set up a physical measurement which would measure either of these two quantities. And kind of instincts tell us, well, if you're a physicist, you want to describe physical systems, because we should not do it with unphysical quantities. In fact, it's not correct, because it's good for general education to understand that it's not correct. And frequently, good news, frequently it is convenient and proper to use some physical values for physical quantities. simplest and kind of emotional example is voltage. Voltage is similar to electrostatic potential. Can one measure voltage? No, one cannot measure voltage. One can measure only voltage difference. So if you have two wires, naked wires, and if you grab one wire, you don't feel anything. If you grab both, you're going to measure voltage difference between these two wires, and it could be quite entertaining. Right. So it's an example of physical quantity which we use, which stands in our electricity bills, but it's not physical. So don't pay your bills. Yes?
It seems a bit inconsistent because why did we consider fields physical in the first place when we only measure forces? Why do we make the separation between apparently not physical when a field is defined by, for instance, force divided by mass?
Just experimentally, so when you make this measurement of force with different charges, you got that there's something in this point of space which produces forces proportional to charges. Another concept.
For potential.
Eh?
So I can say the same thing for potential. It causes measures.
No, one cannot really measure potential because one can always shift all potentials in this world, but by 1 volt, 10 volts, nothing will change. So it's out of our observation abilities. Okay, so why to use it practically? It might simplify the math, and as you will see, it will allow us to make up Hamiltonian very neatly. And yeah, the fact that we have to look at this unphysical variables actually allows us to understand the theory deeper, to understand real structure of the theory. Finally, people came to relativistic formulation, and that all became clear. What is a little bit nuisance? I have to take into account that these things are physical values, and that means it can be chosen in different ways to describe the same physical system. This is called gauge. I don't know why it is called gauge, don't ask me. This is gauge, and this is gauge invariance at the level of Maxwell equations. We will also talk about gauge invariance of quantum equations, Schrödinger equation. That will be something different. Good. What does it mean? It means that for any configuration of A, we can make equivalent configuration by adding to a gradient of arbitrary function of time and coordinate, and we have to correct for scalar potential by distracting the time derivative of the same one. Good. One can check it, one can substitute it in math equations and see that equations do not change. They do not depend on this choice of chi. They do not depend on the gauge. All right. That gives us some freedom. We've discussed about freedom in the first lecture for the course, some freedom in quantum mechanics. That's, for instance, the choice between Heisenberg picture and Schrödinger picture. It's also another example. So different gauges is a degree of freedom we can choose for ourselves. Right, so the gauge invariance is the fact that the results for physical quantities do not depend on gauge choice. Right, two examples of the gauge. Lorentz gauge. You might say I'm a bad Dutch. I couldn't spell Lorentz well, but it's a correct spelling. It just happened to be a different person who worked closely in the same area, thinking about electromagnetism. That was a Dane Lorentz. Right, so he came up with a gauge that was before relativity theory. He just figured it out without Einstein. Right, it is a choice, certain relation between scalar potential and vector potential of this form. That doesn't look very instructive, but again, like many things, you accept it, you work with this, and you got something nice. The resulting equations become nicer. One could say it's a Lorentz invariant, but it's, did I put it correctly? It's Lorentz invariant, it's T. It's, this is due to Einstein, but we call it Lorentz invariant. This is invariance related to special theory of relativity. Fine, what is this funny square here? It's an operator of wave equations, as we discussed in the beginning. Second derivative of time minus second derivative of D'Alembertian. Fine, nice symmetric form. But the point is that we are not spirits, we don't move with relativistic velocities, we're humans, so it is more convenient to use a different gauge, which is called Coulomb gauge, right? And that all simply means that the divergence of vector A is chosen to be 0. Fine. It's good for our world, for non-reducible problems. And what are the questions? That's nice, simple question. No ways. Right. And this is the second equation. Well, it looks a bit more complicated, but okay, let us believe that. But look, I made all exams in my first year, and I'm gonna see a problem with the first equation. What kind of problem? How is related to relativity theory? Let's go step by step. That equation defines the response, which is electric potential on the source, which is particle density. Suppose we have a single charge, particle density. Let's move it a little bit. All right. The problem with this equation is that response is instant. And that is in contradiction to what we've been told. In your first year, nothing can propagate faster than light. Good, sir. What's the solution to this paradox? I want to comprehend it.
we said we would use this for non-relativistic problems, so, and we just.
There's also exact questions, no approximation, right? And there are true questions. There's something about interpretation because
It's the scalar potential and not actually the electromagnetic field.
precisely. So let's not forget that scalar potential is not physical quantity. We cannot measure instant response. If we compute the response of electric field and magnetic field, we're going to use both equations, and that will give us the result, which is satisfactory with the point of view of relativistic theory. Good, that was Coulomb gauge. Now I get back to Bollinger.
Can you explain what do you mean when you say the electric and magnetic fields are nicely separated?
What did you say? Nicely separated?
Yes, I think it was written in the previous slide that the E and D field are nicely separated.
In relativistic field theory, electromagnetic field, electric field looks pretty much the same as magnetic field. Say if you go with a plane wave, then it's just difference in directions. Electromagnetic field are something which moves with speed of light. It's very similar to electric field and magnetic field are very similar. If we talk about our work, the charges move slowly, then there is apparent difference. Electric field produces a force on charge if it doesn't move. Magnetic field comes differently, it comes as a Lorentz force. Those are separated in this form. In this gauge, you see that magnetic and electric field are different things. Fine, okay, boring job. So our task is to present electromagnetic field as a set of harmonic oscillators, similar to what we have done for elastic string. Good. I'm gonna do the same what I did for the string. I'm gonna find first general solutions to these equations. Right. I want to simplify a bit. First of all, I assume that there are no charges. And in this case, if I work in Coulomb gauge, can safely forget about scalar potential, just set it to 0. It's Unphysical, I could set it to any quantity, but I would like to just to forget about this by setting it to 0. Fine. What do I have after that? Oh, it's just wave equation, which remains for vector potential. Could find the solutions of wave equation, and then at next stage, if I want, I can get expressions for electric and magnetic field. Right, but we kind of almost done because we have already solved wave equations. So again, in order to have all solutions, in order to be able to count all discrete cases, we would like to impose boundary conditions, which looks funny for electromagnetic field, but anyway, we will do so. Right, so what are solutions of Maxwell equation? It's very similar to string with one little but important difference. Let me discuss this. Okay, we choose wave vector. It is quantized owing to boundary conditions. We can substitute it to equations and get the dispersion relation between frequency and k, which is very simple now. Right. And let me write it down. It would be logical for me just use vector amplitudes. I do, but I present it a little bit different way. I have vectors E, which I will call polarizations, and scalar amplitudes, A and K. Fine. What about these polarizations? Kind of the reason of thinking about this in this way comes from the fact that I have to satisfy this equation of Coulomb gauge. And that means that for a solution in this form, the direction of polarization must be perpendicular to the wave vector. If when we do calculations with electromagnetic waves, that becomes crucially important, as we see. Right, from three-dimensional space, we forbid one direction. We have two opposite directions, two remaining directions perpendicular to k vector. So for each k, we have two different waves corresponding to two different polarizations. These polarizations can be, as you might remember, chosen in different ways. Could be linear polarizations in perpendicular directions. It could be circular polarization in one direction or another direction, corresponding to complex vectors A. But anyway, what's important for me at this moment, there are two waves, two possible polarizations for each k. So it's a partial solution. Well, what I would do with general solution, I just sum up over k. And here, I want to put that ugly square root again. Here it is, here it stands. So I rescaled amplitudes A's to make them B's, and that expresses general solution for vector potential in terms of normal coordinates. Good. Then again, the question, why do I have to make this transform, which brought the equation to the ugly form? Because I expect to get something nice. Nice is the expression for energy for the Hamiltonian analysis. Right. I wonder if the work put here is obvious. So let me just say in words, step by step, what are the actions one has to take. Right, so one starts with this expression. It's okay, but we have fields here and here. So one has to differentiate these expressions with respect to time, with respect to get electric field, with respect to coordinate to get magnetic field. All right, then we have electric and magnetic field as a function of coordinates. It is a sum of plane waves, and we integrate over plane waves. Right? So each term becomes a double sum over two waves. I just tried on the coordinate dependent part without much coefficients. Okay, it has to be conjugated, so it comes with minus. Good, that looks overwhelming, but now we integrate it. We integrate it over the full space. That's why terms where k is not the same as k prime are just removed by integration. So instead of double sum, we will have a single sum, which is here. Here it is. And we recognize this form. This is the universal form. We have only frequencies of corresponding modes. No details about that. Incredible things, mu naught, epsilon naught. Everything is in the definition of D. Fine. It's also convenient to compute Poynting vector in the same format. All right, we see that the Poynting vector really points in the direction of propagation. That's natural because, yeah, it's energy transfer associated with propagation of light, propagation of radiation. Fine, it's a standard form. Then again, I wanna complete that what I did for the string. I want to get from normal coordinates to generalized momentum and coordinate. That looks like a kind of a misuse in this context. These things are made from electric and magnetic fields, and we would call that momentum and coordinate. Again, the reasoning behind that it's all very similar to mechanical harmonic oscillator. Same structure of equations, same physics, in fact. Good. That's what we did. We introduce real quantities, Q and P, and substitute them again into the Hamiltonian. Fine. That's the energy, and now we see explicitly that this is an energy of a set or big number of harmonic oscillators, each with corresponding frequency omega k. And this is working Hamiltonian. So equations for these variables can be derived in standard way by differentiating the Hamiltonian with respect to momentum and coordinate. So in fact, we have started with 4 maximum equations, and we came to this point now, which There's no information about, there's nothing electrical. Nevertheless, it is correct representation of maximum equations. And that will work for actually any linear field. Right, so now that's the conclusion. Electromagnetic field, as any field, is a collection of harmonic oscillators. I wanna do some simple calculations which will be relevant for us when we talk about decay rates, when we talk about many waves, many electromagnetic waves. Right. First, I wanna understand how many oscillators do I have. Short answer is it's not zero, it's another popular answer, infinity. Right, but that answer is hardly constructive. We just have to understand where we want to have these oscillators, and then we can count them. Right, so let us look at the space of K vector, and let us define a small cube in this space with dimensions dkx, dky, dkz. Right? And now we recall case are discrete, and we just count how many discrete states are there in this cube. It's proportional to the volume of this cube, right? And I shall not forget that I have two polarizations for each K. So that gives me total number of oscillators in this small cube. Okay, it's still infinite, it's proportional to infinite volume of the whole system. Sometimes that is enough, but I'd like to ask another question. I understand that these modes have different energy. I would like to concentrate on energy interval instead of a small cube in K space. So that's a cross section of K space. Energy is modulus of K, so this is equipotential of energy. I want to look at frequency. I don't make a difference in quantum world. I want to look at the small interval of frequencies and figure out how many oscillators are there. Well, I have to do, I can treat it completely geometrically, right? So one just has to compute the volume of this slice in three-dimensional space. Fine. This is what we get when we compute the volume. So that's number of oscillators of electromagnetic field per frequency interval. You see, it also contains speed of light. Good, that we're gonna use a little bit later. We don't need it now. And what I want to do now is to go from kind of fundamental physics to applied physics. Right, it's nice to know that we have infinity of oscillators in our vacuum and our universe. But if you wanted to work with oscillators, you better concentrate on one, which you can control and apply. So how do we make a single oscillator, simplest oscillator? I hope you remember we just put, we just connect capacitor and inductance. Right. Let me recall simple physics of that. First of all, let me recall the energy of the subject. In general formulation, we have integrals of squares of electric fields and magnetic fields. Now for this oscillator, we have a little bit different variables. We have voltage, which drops at this capacitor. And we have current in the coil. Good. So, how to derive equations, how to derive equations of motion? Well, here, owing to simplicity of the problem, we can just use very simple reasoning. We don't need Hamiltonians at this point. Good, so what does it mean, this equation? Who can comment on this? Right, so I is usually current, very well. Current is a derivative of charge. And this is the current of through the capacitor. Oh, come on, capacitor is insulating. How current can go through capacitor? Huh? Do you remember? From my student times, I remember an idiotic joke. So if there's a capacitor, direct current can go through. So it wiggles a bit. It becomes AC current, and then it can go. Right, so AC current can go through capacitor. Fine. So what I write here is just conservation of particles, if you wish. Current is a change of charge, but charge and voltage at the capacitor are related. Okay, it's already working equation. Now, I also want to recall Maxwell induction law. If I change the current through the coil, I'm going to have voltage difference at this coil. Right? Induction voltage. So that's I put as a second equation. Fine. Usually in electromagnetism, you don't regard it as evolution equations, but if you look at it, you understand they are. There are evolution equations for current and voltage, which we can solve. I wouldn't write down the solution, you all know. It describes oscillations with a frequency given by that. So that was about simple oscillation. I have to be consecutive, so I have to, since I promised you to do all this boring exercise for everything, for every field, I've got to do it for this simple oscillator. Good, so let me see how can I figure out what's momentum and coordinate in this case. I'll just start with Hamiltonian equation. Sorry, with a Hamiltonian. That's P and Q are still abstract, but I have a vague idea that momentum is a motion, perhaps it's related to the current. And voltage is something stationary, perhaps it's related to generalized coordinate. Good. So just make an assumption that these quantities are related with yet unknown coefficients. Then what do I do this? I put these expressions into equations which I got and compare it with equations which I derived from Hamiltonian. So two ways derive equations from Hamiltonian and use equations which I obtained at this page. There's no Hamiltonian, just simple cheating. All right. So if we compare it, we can figure out what is alpha and what is beta, and find the coefficients which relate generalized momentum and current, and generalized coordinate and voltage. Here they are. So we have quantized we haven't quantized it yet. We have reduced single oscillator to general scheme. We can write down normal coordinate. Right. Good, we've done what we can do for fun. Now we can associate oscillators in vacuum in of oscillators of Maxwell equation with capacitances and inductances. For each oscillator, one can figure out effective capacitance and inductance just employing these formulas. Okay, here how they look like. So capacitance is proportional to the length, big length of the whole system, and is the same for all oscillators. That's also associated. Good. I guess I'm done with this classical physics part. Next time we will quantize oscillators, so it will be rather steep, but pretty straightforward way because we know how to quantize single oscillator. Thank you for your attention. Are there any questions? Not at the moment. Good, then see you again.